Welcome and thank you for waiting. All participants will remain in listen-only mode for the duration of today's webinar. Today's webinar is being recorded and will be posted publicly. If you have any objections, you may disconnect at this time. I would now like to turn over this session to your host from the U.S. Census Bureau, Caleb. Caleb, you may begin.
Thanks, Anthony. Hi, everyone. Welcome to today's presentation using American Community Survey, or the ACS, Estimates and Margins of Error, or MOE. My name is Caleb Hopler, and I work for the American Community Survey Office here at the U.S. Census Bureau. I'm excited to share information about the ACS, its data, and the margins of error that it provides. So if you have questions, you're welcome to submit them using the Q&A feature here in WebEx. My colleagues will try to answer them during the webinar. The PDF version of the slides is available, the link, if you'd like to download and look later or follow along today. And also today's webinar, like Anthony said, is being recorded. The recording will be available online at this link later after the webinar. So let's jump in. So yeah, today's webinar and presentation will start with a discussion of ACS estimates and overview. Then we'll get into what a margin of error, or MOE, is, and then I'll explain why it matters. Next, I'll discuss statistical testing, more specifically why statistical testing is important and how it uses margins of error. We'll then go over a few special cases where the MOE is presented differently, and we'll walk through an example of how to approximate the MOE for a combined estimate. And finally, I'll share some available resources for learning more beyond today's presentation. So the American Community Survey, or ACS, is the premier source of detailed information about the nation's people and housing. The survey samples approximately 3.5 million addresses each year and 150,000 group quarters residents. These data are collected continuously throughout the year to produce annual social, economic, housing, and demographic estimates for communities throughout the 50 states, DC, and Puerto Rico. Now, the estimates cover more than 40 topics. The ACS collects this detailed information each year that was previously collected by the decennial census each decade. So information from the ACS generates data that help inform how trillions of dollars in federal funds are distributed each year, supporting more than 300 known federal uses and countless non-federal uses. Now, ACS data are timely because they are released the year immediately following the year in which they are collected. So this means that the ACS creates period estimates. They represent the characteristics of the population and housing over a specific data collection period. The ACS releases estimates for 1-year and 5-year periods. After years of extensive testing, the ACS was fully implemented in 2005. So the first ACS 1-year estimates were collected in 2005 and released in 2006. The first 5-year ACS estimates were collected between 2005 and 2009. And then released in 2010. So you all are likely aware of the decennial census that occurs every 10 years, where everyone is asked to respond. And the data shows the official count of all persons and households in the United States. Now, as mentioned, each year, the U.S. Census Bureau contacts over 3.5 million housing unit addresses to participate in the ACS. Now, since this number is only a sample of the entire population, the information obtained from this sample is then used to estimate characteristics about the total population in a timely and cost-effective manner. These are only estimates and differ from those that would be obtained in a decennial census if we were to ask the question to everyone in the country. Also, in an estimate based on a different sample, 3.5 million addresses could also differ. So this results in an element of uncertainty in the data. So this is where MOEs, margins of error, come into play. So if you are interested in more information about ACS sample design, I recommend reviewing the ACS Design and Methodology report found at the link on this slide. So let's go over a few key points about the data before jumping into specifics of the MOEs. The ACS provides three main sets of estimates: the 1 year supplemental, and the 5-year estimates. So these data products are released about 1 year after the data are collected. ACS data are generally released in September, the calendar year after collection, as 1 year estimates. In October, calendar year after collection, as 1 year supplemental estimates. And 5-year estimates are generally released in December, the calendar year after collection. So for example, the 1 year ACS data collected from January 1st through December 31st of 2024 were released September 11, 2025. So ACS 1 year estimates, which combine data collected over 12 months, are available for geographic areas with a population of 65,000 or more. ACS 1 year supplemental estimates are a set of simplified tables of detailed tables that are available for geographic areas with populations of 20,000 or more. 1 year supplemental estimates are simplified versions of popular ACS tables and provide the most current data to almost twice as many geographies compared to the standard 1 year release. ACS 5-year estimates combine data collected over 60 months, are available for geographic areas of all sizes down to those granular census tracts and block group levels. The full detailed data release schedule for each year is available in the link you see on the slide, which you can also navigate to by visiting census.gov/ACS. Now, ACS provides data from more geographies on an annual basis than any other household survey. The image on this slide shows some of the geographies for which ACS data are produced and the relationship between them. So you'll notice that the larger geographic areas are at the top in the center, such as nation and states, working downwards to the smaller geographic areas, such as census tracts and block groups. Broadly speaking, the size of the margins of error relative to the size of the estimate increases as the size of the geography decreases. So for example, the MOE for a block group estimate is likely relatively larger than the MOE for a corresponding state estimate. So, okay, what is margin of error? Let's get into that now. So because the ACS is based on a sample rather than all housing units and people like the decennial census, ACS estimates have a degree of uncertainty associated with them called sampling error. In general, the larger the sample, the smaller the level of sampling error. So to help users understand the impact of sampling error on data reliability, we provide a margin of error for each ACS estimate. Put simply, an MOE is a measure of the possible variation of the estimate around the population value. MOEs allow data users to be certain that at a given level of confidence, the estimate and the actual population value differ by no more than the value of the MOE. The Census Bureau uses a 90% confidence level as its standard. All ACS estimates published on data.census.gov have margins of error calculated at the 90% confidence level. It's also important to note that the MOEs provided by the Census Bureau are always in the same unit as their respective estimates. So for instance, a percent estimate will have a percent MOE, and a median income estimate will have an MOE in dollars. So here we have a typical table, subject table S0101, which is the age and sex table, as it is displayed on data.census.gov for the state of Maryland using 2024 ACS 1-year estimates. I have the row I'm going to work with highlighted, but let's go over some of the basics first of the table. As you can see, the table has three elements: the characteristics, aka the descriptions like male, total population, under 5 years, etc., the estimate, and the accompanying margins of error. So in this example, we want to know the number of males under age 5 who live in Maryland. We find the lower bound by subtracting the margin of error from the estimate. Similarly, we find the upper bound by adding the estimate and margin of error. So we are 90% confident that the true number of males under 5 in Maryland falls between the lower bound of 174,797 and the upper bound of 179,297. So you might be wondering, where do the MOEs actually come from? It is actually one member of the family of measures of sampling variability. This slide shows you how one can be derived from another. At the top is the variance. The variance is calculated for each estimate when the estimate is tabulated. The standard error, or SE, is found by taking the square root of the variance. The standard error gives a clearer picture as to how much variability is in the estimate, as it is in the same units as the estimate itself. The standard error is used to calculate the margin of error, or MOE. So then this calculation changes depending on the confidence level. So to calculate the MOE at Census Bureau's standard 90% confidence level, the SE is multiplied by the critical value of 1.645. Now, sometimes you may want to use a confidence level other than the 90% census standard with your ACS estimate. So for instance, you may wish to use a confidence level of 95% or 99%. Let's go over how to convert from one confidence level to another. Now, first of all, to calculate a margin of error at a given confidence level, you multiply the critical value by the standard error. The critical value depends on the confidence level you are seeking. So let's use the example of converting an MOE at a 90% confidence level to 95% confidence level. To make things visually clearer, I've gone ahead and highlighted the 90% level and its critical value in green, and I've highlighted the 95% confidence level and its critical value in pink. So again, to calculate the MOE for ACS estimates, we multiply the standard error by 1.645, which is the critical value for 90% confidence level. As you can see, the MOE for the 95% confidence level is equal to the standard error multiplied by 1.96. So to convert from a 90% confidence level to a 95% confidence level, simply multiply the ratio of the new confidence level to the old confidence level by the MOE, as shown in the formula. It may be easier to think about it step by step. First, this formula divides the current MOE by 1.645 to convert it back to the standard error. Then the standard error is multiplied by the new level of 1.96 to find the MOE at the 95% confidence level. So for an illustration, let's look at what our number of males under 5 years in Maryland estimate from table S0101 looks like at a 95% confidence level. The MOE from data.census.gov is currently at a 90% confidence level. To convert, we multiply the MOE by the critical value ratio of 1.96 over 1.645 to get a new MOE of 2,681 after rounding, which is the MOE with a 95% confidence level. As you can see, as the confidence level increases, the MOE increases. This is especially clear when we add the 99% confidence level. At the 90% confidence level, the MOE is plus or minus 2,250, whereas at the 99% confidence level, the MOE is plus or minus 3,529. Now, in other words, to gain more confidence, we must allow for more variability in the data. So now we know what MOEs are and how they're calculated, but you may wonder what this means in a practical context. Why do they matter and what can they be used for? Let's get into this now. One way to use the MOE is to construct a confidence interval. Confidence interval is a range of values where at a given confidence level, you can be certain the true population value lies. You might have noticed that our MOEs are always displayed with a plus or minus sign. So this is a good clue to remember that the estimate plus or minus the margin of error provides the confidence interval. Now let's look at an example of a hypothetical block group. Block groups are the smallest geographies for which ACS estimates are available. Now, our hypothetical block group has a median income of $37,284 and an MOE of $20,922. The upper bound is the estimate plus the MOE, or $58,206, and the lower bound of the confidence interval is the estimate minus the MOE, that is $37,284 minus $20,922 to get a total of $16,362. Now, this confidence interval is at the 90% confidence level, the Census Bureau standard. So therefore, we can conclude at a 90% confidence level that the true estimate for the population lies somewhere between those two values. The MOE can also allow you to see if there is enough evidence to conclude the estimates are statistically different from one another. So as an example, let's compare that hypothetical block group we just looked at to 4 more hypothetical block groups. With just this information on the screen, the estimates alone, you probably conclude that the block group 1 has the lowest median household income of $37,284, and that the block group 5 has the highest median household income at $76,850. However, we are missing some important information in the MOE column. So adding in the margins of error to the table, we see a different picture. As a note, if you as a data user work with data, particularly at lower levels of geography, you may find instances with high MOEs. In this hypothetical example, the MOEs for these estimates are high. Not all of the medians at the block group level have such high MOEs in ACS data, but it is important to be aware of the MOE when looking at an estimate. So looking back at this table, we can now see that the median we thought was the lowest has an MOE of $20,922. Meanwhile, the seemingly highest median has an MOE of $47,200. So both estimates, therefore, have substantial variability. Unless you take into account these MOEs, you cannot conclude that they are statistically different from one another. Instead, you have to do statistical testing to check for any differences. Now, no worries. I will show how to perform statistical testing using this exact example soon. But first, with a good sense of what an MOE is and why it should not be ignored, let's get into how MOEs can be helpful to your data analysis by looking at the statistical testing. Now, statistical testing is an important part of data analysis as it can tell us whether or not a difference in estimates is likely to be real. So in short, a statistical test is a test to determine if a difference is unlikely to have occurred by chance. To be significantly different, there must be a statistical evidence that there is a difference between two estimates. Statistical testing should be conducted anytime you make a comparison between two estimates. So for example, if you're going to the city council or county council, asserting that a certain population has experienced poverty in higher proportions in recent years than it had in the several years before, you want to make sure you've tested to know that a true difference exists. Or if you're the transportation planner in your county and you want to make the case for projects based on perceived longer commute times, you want to conduct statistical testing before proceeding with project proposals to confirm that the estimated commute times have actually increased. This slide contains the formula for testing statistical significance. So some good news for you. You don't have to worry about relearning advanced algebra because the Census Bureau provides its statistical testing tool free for public use. This tool allows you to input estimates you'd like to test and receive a visual notification of whether the estimates are statistically different or not. Using this tool, you can compare both pairs of estimates and groups of estimates against each other. The tool is available for download as an Excel spreadsheet via the link at the bottom of this slide. So here's a screenshot of the statistical testing tool. It's an Excel document with an overview tab, instructions tab, two tabs for testing, one for testing pairs of estimates and another for multiple estimates at a time, plus a work example tab and a contact us tab. Now each of the two testing tabs also have instructions at the top, plus columns for a testing label, the first estimate, the first MOE, the second estimate, and the second MOE. This tab can compare up to 3,230 pairs of estimates at once. And results are both written and color-coded. Estimates that are not significantly different will have a red no in the statistically different column. That is described in text at the top of the spreadsheet. Multiple pairs of estimates can be compared at once. The same tab can compare estimate pairs of differing types. So let's run through a quick example here. For our testing, let's first look at a selected population profile, table S0201. Note that prior to my taking a screenshot, I had actually scrolled down a bit in this table. So suppose you wish to compare the median age of the total population in the US to the median age of the total population of New York State. This example uses 2024 ACS one-year data. So the median age for the US is 39.2, while the median age for the total population of New York is 40.1. To be able to say that the median age for the US is different than the median age for New York, we must first complete statistical testing. So I pull up the statistical testing tool spreadsheet and open the tab stat test for two estimates, because we are only comparing two estimates at a time. So in the first row, I've input our median age estimates and their corresponding MOEs into row 1. With a yes in the statistically different column, the spreadsheet confirms our results that the estimates are in fact statistically different. Now, I've also input the hypothetical block group level median household income estimates in row 3 that we looked at before. So if you'll remember, after looking at the margins of error, we couldn't tell if the first block group estimate of about 37,284 was significantly different from the fifth block group estimate of 76,850. So to check this, I've manually input them into the spreadsheet here. The red no in the statistically different column tells us that they are not statistically different from each other. Now, if you wanted to compare all 5 block groups from our hypothetical example to each other, you could individually put the combinations into the two estimates tab, or simply you could use the multiple estimates tab of the spreadsheet. So this tab can compare up to 150 estimates against each other. However, this test can only complete one type of comparison. So for instance, medians and counts cannot be compared at the same time. Medians with medians or counts with counts. So here I've input our hypothetical block groups into the multiple estimates spreadsheet tab. As you can see, the format is slightly different from the last tab. Each table corresponds to only one estimate and MOE. The spreadsheet then creates a grid of results in which each estimate is compared to the others. A comparison of an estimate to itself is noted by a gray square with an X. When statistical testing is inappropriate, a gray square with a dash through it will appear. Otherwise, the notations are the same, with significant differences denoted by a white square with yes, and a non-significant differences denoted by a red square that reads no. A key of these notations are given at the top of the spreadsheet for reference. So here we can see that none of our hypothetical block group estimates are significantly different from each other. This is due to their large MOEs, which we had actually saw earlier. So now let's say that even though you do have the Census Bureau's statistical testing tool available for you to use to assist with statistical analysis, you still want to perform the testing yourself. Great, let's walk through that together. The formula shown earlier uses standard errors. On the screen now is the generic statistical testing formula, the Z-score formula, that has been modified to use MOEs instead of standard errors. Now, this was done to make the formula easy to use, and because the MOEs are conveniently published in the ACS data tools, such as data.census.gov. Now, this formula uses both the estimates and the MOEs to generate a result. If the result of the formula is greater than 1.0, then the estimates are statistically different at a 90% confidence level. Let's walk through an example to see how testing is done. Let's use the same median age estimates and their MOEs we used in the example with the statistical testing tool. So to begin our testing, we first take the difference of the estimates, 39.2 minus 40.1. For the second step, we take the absolute value of that difference. In step 3, we square the MOEs of each estimate. For the US MOE, 0.1 squared is 0.01. For New York MOE, 0.2 squared equals 0.04. Next, we add the squared MOEs together. So that is, we add 0.01 to 0.04 and obtain 0.05. For step 5, we take the square root of the sum of the squares from step 4. So in this case, the square root of 0.05 is 0.224. We then divide the result of step 2 by the result we found in step 5. So that is, we divide 0.9 by 0.224 to obtain a value of roughly 4.02. So in step 7, we compare our result to 1.0. Since 4.02 is greater than 1, we can say with 90% confidence that the median age of the population of New York is statistically different than the national median age. So put it all together. Here's the generic formula in our worked example. Again, as 4.02 is greater than 1.0, we can conclude with 90% certainty that the two estimates are statistically different. Now, the nice thing about the Z-score formula is that you can use it to compare a wide range of estimates, including estimates between different years, multiple year estimates between different non-overlapping time periods, estimates across geographic areas, and estimates between surveys. It can also be used to compare an estimate against a fixed threshold. So for example, to test if the estimate is above 25%, and in this comparison, the MOE of the threshold is always 0. Now keep in mind that single year and multi-year estimates should never be compared in your data analysis. So comparisons between 1 year and 5-year data products will yield erroneous findings. Therefore, only compare 1 year with 1 year and 5-year with non-overlapping 5-year estimates. So for guidance in comparing ACS estimates, refer to the link at the bottom of the slide. Now, some tables provide visual cues of statistical significance. The first type is the comparison profiles. Comparison profiles are similar to the data profiles you may be familiar with, except they include estimates from prior years. The estimates from prior years are inflation adjusted. Now, there is also an asterisk in a column next to the estimate if the estimate from the current year is statistically different from the prior year. Now, this is explained in the table notes found by clicking the notes icon. So for example, average household size of 2.53 in the 2020 to 2024 estimates is statistically different than 2.62 in the 2015 to 2019 estimates. This slide shows, what the slide shows is a 5-year comparison profile that compares 2 consecutive non-overlapping 5-year data sets. Comparison profiles for 1-year data are also available. The comparison profiles are available for a wide variety of geographic areas, including the nation, the states, counties, school districts, and congressional districts. Now, another product type that includes statistical testing are the ranking tables. Ranking tables show you how the nation and different states compare to one another for about 100 characteristics across topics. These tables are not found in data.census.gov, but rather through the ACS website. If you want to learn more about how to calculate statistical comparisons using ACS estimates, please check out a recorded webinar we conducted highlighting best practices when using ACS data. Now, I hope you have some familiarity with statistical testing and some of the various tools and products available to you. However, there may be times when you come across something that might look a little odd on data.census.gov. You might not know how to proceed. So we'll explore how to deal with some of these special cases now. You may have noticed in an earlier screenshot some asterisk in place of a margin of error. So here's that screenshot, and it highlights our first special case, a controlled estimate. Certain estimates in the ACS are controlled to match the official population estimates. If this has occurred, then the MOE will have 5 stars or asterisk instead of a number. You may use this estimate in a statistical test. If using the formula, simply set the MOE to be 0. If you are using statistical testing tool that we offer, you can simply paste in the 5-star notation. The spreadsheet will convert it automatically. Now, another special case is for estimates which are 0. Here we have an example of table B01001E, which includes many 0 estimates for the geographies chosen. As this table demonstrates, 0 estimates have non-zero margins of error. This is because the ACS is a survey. Households with rare characteristics may not be surveyed, but may still exist. There are also special cases for which statistical testing is not possible. Table B06011 for Enoch City, Alaska, using the 2012 to 2016 ACS 5-year estimates as an example, gives us an illustration of these cases. Medians and aggregates with too few observations are noted in data.census.gov as an estimate with a dash and an MOE with 2 asterisks, which you can see for the characteristic native, born outside the United States. Values are not displayed to protect confidentiality. If a percent or ratio has a denominator of 0, it will also show a dash for the estimate and 2 stars for the MOE. Medians and the highest or lowest interval of an open-ended distribution also have a different notation in data.census.gov. These estimates will be followed by a plus or a minus sign with an MOE of 3 stars. So looking back to the table, we see that the foreign-born characteristic is at the lower median interval. We can tell this because the estimate is not a number, but rather a combination of a number and the subtraction sign. So in this case, 2,500 minus. The minus sign tells us that the median is less than the number that precedes it. For foreign-born persons, we know that the median income is less than 2,500. Due to the methodology we use, the actual median for these cases cannot be calculated. A median at the upper interval would be displayed similarly, but with a plus sign following the number. The MOE would still be 3 stars, and all you would be able to say about a median with an estimate on data.census.gov of 250,000 plus is that it is above $250,000. So explanations of the table notations can be found by clicking the notes icon above the table. Also, statistical testing cannot be performed for either of these cases. However, all notation is recognized by the statistical testing tool that I demonstrated earlier. So for instance, these cases will tell you that testing is not appropriate. There are also other data tools to obtain the ACS data, such as through my tribal area, which provides ACS data for American Indians and Alaska Native areas, or through the Census Application Programming Interface, or API. The special cases for ACS may be displayed a little differently, but the documentation for each application will explain what you are seeing. The special cases are the same as the ones that we have been discussing. In addition, some estimates have an MOE that is larger than the estimate itself. This occurs mainly in estimates for small geographies or small groups of people or households which have a small sample size. So as an example, we have table B17001, which is showing the number of people above and below the poverty level by age and sex at the tract level. Tracts are one of the smallest geographies that are available on data.census.gov for ACS data. As you can see, many of the MOEs here are larger than their respective estimates. Data users should exercise caution when using these estimates because they have questionable reliability. Large MOEs can also signal that the sample size for the estimate is small. There is not an ideal solution to dealing with large MOEs. However, a few workarounds are available. One method is to use a larger geographic area. So for example, you could use county estimates in lieu of tract estimates. Another method is to form larger groups by combining estimates or geographies. So in doing this, you'll have to approximate the MOE for your derived estimate. So that brings us to our next section, approximating the MOE. So let's start with a simple example of how to derive a new estimate. Here are some age groups by sex. Same table. Top image shows males under 5 years of age. Second image collapses males to show females under 5 years of age. So suppose you want to know the total population who are less than 5 years old. Now, the first thing you want to do is check for other tables that may have your estimate already that you're wanting to derive. But if there aren't any, then we'll proceed to derive. To find this estimate, sum the estimates. Approximating the MOE takes a little bit more work. Similarly to what we did for the example with the z-score, you must square the individual MOEs, sum them together, and then take the square root. Here we have the worked example. To obtain the total number of children under the age of 5, we sum the estimates for males and females, which gives us 18,365,047. To approximate the MOE, we first square the MOEs, then we sum the squares. In this case, we're adding the square of 21,642 to the square of 18,211. Now finally, take the square root of the sum to obtain the MOE. So here, our MOE is roughly 28,285. Advanced users may also be interested in using the variance replicate estimate tables. The variance replicate estimate tables include estimates, margins of error, and their corresponding 80 variance replicates for selected ACS 5-year detailed tables. These tables can be used to calculate MOEs for derived estimates in the place of the MOE approximation method that I just demonstrated. So using these tables, the calculated MOE will include the covariance, which is the element that is missing from the approximation method. In the interest of time, I'm not able to get into what covariance is. However, I will say that if the covariance is large, the approximation could be very different from the actual MOE. The variance replicate table provides users a means to calculate the actual MOE. Using these tables requires a fair understanding of statistical programming. So for more information, please follow the link at the bottom of this slide. I'd also like to note that for some detailed tables, a collapsed version is available. So here we have an example. On the left is the table B01001B, while on the right is the collapsed version, C01001B. The detailed table will have a table ID which begins with a B, while the collapsed version's table ID begins with a C. This example is for sex by age for persons reporting a race of Black or African American alone. The alone means the Black African American was the only race reported. So as you can see, you do not have to approximate the MOE for collapsed tables, as it is provided for you. The categories were created by subject matter experts. If the categories are not exactly what you want, they will at least allow you to combine fewer estimates together. So here we see that the age categories have been collapsed into those under 18, 18 to 64 years old, and 65 years and over. So now let's talk about the variety of resources the Census Bureau provides for learning more about ACS data, MOEs, tools, and about the survey at large. Best starting place for any ACS related resources is the ACS website, census.gov/ACS. This website contains a wealth of information about the survey, data products, tools for data users, and other helpful information. Our MOEs are, of course, found alongside the data. ACS data tables and tools can be found through the ACS data page. So these web pages will introduce you to the most popular tools and data products with descriptions and links for each. Some tools show MOE automatically, like My Tribal Area or data.census.gov. Other tools, like My Congressional District, default to data without MOE shown, but you are able to toggle them on by the MOE option on the tool. For users that have accessed the data but need more information to understand the tables and complete their analyses, we offer instructions for applying statistical testing, accuracy for the data, and much more in our technical documentation section. The instructions for applying statistical testing document provides information on how to derive your own estimates for counts, percentages, ratios, etc., and how to approximate their MOEs. The accuracy of the data document provides basic explanation of the sample design, estimation methodology, and accuracy of the data, whereas the worked examples for approximating margins of error document provides the same equations as the instructions for statistical testing document, but also provides some worked examples. So note there is an accuracy document for the 1 year and for the 5-year estimates. Two are needed because the 5-year document covers issues that are different from the 1 year. So for more technical information on the ACS and how the MOEs are created, you can look at the design and methodology report. Information concerning variance estimation can be found in Chapter 12. We also have a general handbook for data users. Error, statistical significance, and calculating measures of error for derived estimates are found in Chapters 7 and 8, which also show approximation formulas and examples. So before I wrap up, I want to invite you all to keep in touch with us. One way is by sharing your ACS data story. This allows data enthusiasts across the country to share the creative ways they are using the ACS data to make a difference in their community. So if you are someone who has used ACS for your community, organization, or your business, consider submitting your story today. You can also sign up for and manage email updates from us here at the ACS. Our monthly events and updates email will alert you when new materials are available, and you'll stay updated on our data releases. So in closing, let me share information on how to find answers and get support after this webinar concludes. Visit our website, census.gov/ACS. Great resource with information about the survey, data products, tools for data users, and other helpful information. So if you have a question about the ACS, do not hesitate to send us an email at acso.users.support@census.gov or call the number on the screen. Census Academy is our learning hub for data skills. You can learn how to access and use Census Bureau data your way through our how-to data gem videos and in-depth courses, webinars, and tutorials. This page also has a link where you can request a training at no cost from our Data Dissemination Specialists, or DDSs. DDSs are located within your region, can provide you with assistance about Census Bureau data, such as how to obtain or understand ACS data. So whether conducting one-on-one webinars with business startups or conducting large-scale presentations at universities, these specialists strive to put the public in touch with the data that they need. And if you're on social media, connect with us at at U.S. Census Bureau using the hashtag ACS data. And one last thing, if you're using ACS estimates, make sure to source the Census Bureau American Community Survey as to where you received the data. It helps people know that the information that they're using is powered by the ACS. Well, this concludes today's webinar on ACS and its MOEs, or margins of error. Thank you so much for spending this last hour with me, and I hope you enjoyed it. Anthony, I'll go ahead and pass it over to you to conclude the webinar. Thank you.
Thank you all for your participation and engagement in the question and answer. Have a great rest of the afternoon. You may disconnect at this time.